Hello everyone. In this video, I'm gonna talk about one last algorithm I'm gonna be showing you for path planning, and it is called the tangent bog algorithm. Related to this one, we have algorithms called bog1 and bog2, which are quite similar, but they are not as good as this one. This one is clearly outperforming those, and you can just search them, bug1 and bug2, or I can tell you briefly what they are. What this tangent bug does and what makes this one different, or distinguishes between this one and the rest of the algorithms we have seen, artificial potential fields, PRM, and A star, is here you do not have the global map. You do not know exactly what you are going to be facing, where the obstacles are. You can only rely on a range sensor. That's what you can do. You have a device that can give you a range, a distance to the obstacle that is right ahead of you, and you might be right colliding into it, hitting into it. So you have a local limited amount of range sensing that you can do. So your LiDAR or radar or whatever device that you have is not going to just sense all the way to the goal. It can only do some local sensing. It has a limited range. And all you need is one single global goal that you want to go from start to the global goal, okay? And this happens a lot, right? In the environments with uncertainty, because the nature of the environment is dynamic. For example, when you are trying to go into the street and go from point A to point B, there are people moving, there are cars, there are all sorts of things that were not there, or the GPS might not show them, but they just right all of a sudden just appear in front of you, jump in front of you. So you need to rely on your sensors, range sensors, to not have any collision. Okay? Or sometimes you have a mix. You have some map and you have your sensors and you want to combine. So what you do in these self-driving cars is a little bit better than tangent bike, because you do have the start point and the goal point. So your algorithm might do what? Something like A star in the beginning, but it cannot do 100% reliance on that map. It has to modify that map whenever something dynamics changes the path and jumps in front of the path, and then you have to maneuver around it. Okay, so you have to keep updating your map. But in this case, we assume the objects are stationary, but we don't know their shapes, their locations. We just move forward whenever we hit to an object, or we feel like we are hitting, not we hit really, we sense it using our LiDAR, radar, whatever. We try to go around it and keep going toward the goal, okay? So as I said, this method is based on two algorithms called bog1 and or bog2. And what the bog1 and bog2 do, so in bog1, if you have an obstacle like this, and this is your goal. So here I just make it very simple. And this is your start point. What this method does, it goes from start and gets close to the obstacle. How does it go? Along, of course, the line that directly connects your start point to the goal point. So it tries to move along this vector like this. But when it comes right here, it knows it cannot move any further. So first goes along this path, then what? It tries to circumnavigate and goes around the obstacle one complete round. So it does what we call wall following or boundary following. It does one full revolution, and in each one of these locations, based on the sample time that it has and how fast the range sensor can, how fast your computation can calculate the distance at each one of these points around the boundary. It measures the distance from that point to the goal. So it measures this distance, right? This one, this one, this one, this one, so on and so forth. It measures all of these distances, all of them, keep them in the memory, and then comes and now search into these distance values for the minimum one. And it finds that, well, out of all these distances, when I was right here, that was where I was the closest to the goal. So now what? Continues from here, go back one extra amount and goes back to this point, which was the closest it recorded to the goal, and now from that continues on that connecting line, and then what? Goes to the goal. So it's one extra round of motion around the boundary before making any decision, right? So you see clearly how much it has to go. It's like this, going all the way, coming back, and then this extra amount to go back at a point that you already visited. But you make an informed decision because you have all of the D's. So this is called BOG1 algorithm, okay? There is a BOG2. BOG2, this is kind of more similar, this tangent BOG to BOG2. So what you do in BOG2 is, if I can copy this, there we go, and I can put the goal again back at kind of same relative position, and the start at again kind of same relative position. So what you do is, again, you care about this vector, and you go from start to this point, then keep going around the obstacle. But when you're navigating around the obstacle, whenever you meet the line, the initial line that was going from start to goal, whenever you reach that line, you stop. You don't keep going around the obstacle again. You stop there, and now you keep going through the goal. So absolutely, this BOG number 2 is way more intelligent, and it is way faster. Now, there are some scenarios where BOG1 can be better than BOG2, and that's like this second example here I made for you. So here, if you want to go from start to goal using BOG1, so you go all around, right? And you measure all of the distances, and then you remember, well, it was here that I was the closest to the goal. So what would you do? You go one more round, and this time when you reach that location, you stop, and then you go from there to goal, right? So this is the whole distance you travel, twice or 1.5 times kind of around this obstacle plus this initial distance, right? Now compare that to BOG number 2. So what happens in BOG2? So let me get rid of these guys so you can have something for comparison. So in BOG2, you go here, you go around, you come here, and then you meet this line. Now, when you meet this line, you go along the line like this, and then now you have to decide which direction you want to go. If you have an intelligent way to tell you go to the left, that's awesome. But if you don't, one of the things they typically do is whatever direction they circumnavigated the first obstacle, they try to keep that direction. Here, if you look at the direction of circumnavigation, you see it is counterclockwise. So what they might do is go counterclockwise again, because they have no way to decide. And they here they do not have the range sensor that might be able to look at the two endpoints here. Like, let's say it can scan this range and then decides between these two. So if you don't have a way to decide which way to go and you want to keep going counterclockwise again, then you go this direction again, right? And now what? Now you have to go all the way up, go around, come around until you meet the extension of this line, which is up there. So you do wall following, you reach there, and now you go to the goal. And now I bet you this distance that you see over here is more than going twice or 1.5 times around it. Okay, because this object is large and I was stranded all around that object until I could get to somewhere along the extension of the line where I can continue, because I met that extension of the line up here, right? I met that here, but I could not go anywhere from there. There was no clear path to the goal, so I have to keep wall following. And now you see bug 1 can be better than bug 2, but most of the times, 95–90% of the time, unless you have complicated cases like this, bug 2 is superior to bug 1. Okay, now what is tangent bug? So tangent bug tries to be a little bit smarter and also uses a range sensing device. So here, if we go back, and I added some more pictures for you to illustrate that better, what this method does is, first of all, it has a function to minimize, and it is very similar, or I would say to a good extent identical to what you had in A star. So you have a heuristic function that is the cost of going from your location to the goal, and that is basically what? Sum of two distances. One is a distance to go from your location to a point between your location and the goal n, and then the cost of going from that n to the goal. So if you cannot directly in one single step go to the goal, and most of the time you are far away from the goal that even if you want to travel in a straight line, you cannot go in one single step. So you have to go from your current point x to the next point n. And so what you try to minimize is how much it takes me to go from here to the next point, and then how much it takes me to go from next point to the goal. Let's try to minimize that, right? And but I also have a sensor, a range sensor, and for many cases where I'm doing the wall following, basically this distance dx and n that you see here comes from the range sensor. Why? Because I do not have a clear path to the goal, right? So this distance d is the distance between you and one point on the boundary, which is sensed by your LiDAR or radar, and this distance d of ng is mathematically calculated. So using your LiDAR, you can calculate location of point RP1 and RP2, these endpoints on the wall. Once you calculate their location based on the angle and the distance from point P to those points, and based on the current location of the P, then you can find the distance from RP1, RP2 to the goal, and then see which one of those two distances in red, when added to the corresponding distance in green, which one of these two sides basically is smaller, so you go to that endpoint. Okay, so again, we have two general modes of motion: moving straight toward the goal and then wall following. So let me explain that. So the algorithm is like this. If there is a clear path toward the goal, keep going straight to the goal, right? So when I start here, and let's say my range sensor can only measure a circle like that much. That's all my range sensor can measure. Right now, my range sensor cannot identify any object inside that circle. And most of the time, your range sensor is not scanning all 360. Sometimes it does, sometimes it doesn't, right? So sometimes all your range sensor can measure is probably maybe like 100, 120, 150, 180 degrees or so on. It's not going to scan all around you unless it's what? A spinning sensor, like a scanning LiDAR. Yes, they go and scan all around you, but when you're going forward, unless you want to make sure nobody is hitting you from behind, it's just a static environment, right? Then you might just go straight. But of course, if you remember, we said tangent block in general might or might not have static objects. The objects could be dynamic, so maybe there is something from behind that is coming and hitting you. Then having a scanner that can scan behind you is good, so if something is getting too close to you, get out of the way. But for now, let's say there is no collision danger from behind. And so again, it might not be this whole circle that you scan, it might be only a portion of it like this, just a slice, correct? So now your sensor does not sense anything around inside that circle or inside that slice. So say, hey, keep going straight. So from this point, you directly connect it to the goal like that, and go as much as now you get to this point H1, and now when you are in point H1, now your sensor can sense this boundary here. Now you are sensing the boundary of an obstacle, and you know that if you want to go straight along the same line that you used to go, you are going to hit something, right? So now you have to decide how to continue from this point. Now that you are here, now how do I decide where to go and how to go? So what you do here is to explain that for you, I need to define two distances. One is called d minimum, the other one is called d leave. In some other literature, you might see d minimum to be also shown with d followed, and this d leave to also be shown with d reach. So if you see these two other notations for these two parameters, they are the same thing. Okay, now what are these? Well, d minimum is the minimum distance you have observed so far on the boundary, is the minimum distance on the boundary that you have sensed so far, not the entire boundary, only the part of the boundary that you could have sensed, you had the chance to sense. This is the minimum distance from any point on the boundary that you sensed to the goal. Okay, so if you look at this picture, it might be a little bit nicer to see. So here I'm going from this point, I'm starting to do the wall following. And when I go along this path at different locations, right, if I can find the location that I'm currently at using odometry or any type of sensor, then from each one of these points, I try to find their distance to what? To the goal. And then among these distances, see which one so far that I could calculate. So you have to constantly calculate the distance of your current location to the goal and record it in the memory. And now you go and look into your memory and see which one was the smallest that so far you could have achieved, and you call it what? The minimum distance you have observed so far between the boundary and the goal. You call it d minimum. What is d leave? Leave here is, there are two definitions for the leave. One is the minimum distance between the sense boundary at the moment and the goal. So if you remember, d-min was whatever you had so far, it's what you have at the moment. So if you look here, At this moment, this is my robot. This guy here in yellow is all the robot can scan. So this is the boundary that it can sense. Along this boundary, there is one point that has a minimal distance to the goal, and that is this point. So this distance is going to be dleave. What is minimum? Minimum is everything in the memory, right? It's this one. Typically, your d minimum has to be less than or equal dleave, right? Correct? Because that's the smallest that you have found so far, right? Correct? That's what you have. Unless now you end up with the point that now what you can see from the current point of the boundary to the goal is less than this, then it means what? It means now you are at the point that if you go directly to the goal is better than wall following, then you have to stop wall following. Okay, and that's what I mentioned here. You stop the wall following where your leave distance that now you can sense is less than what minimum value that you had so far is less than that. So now you have a good shot at directly going to the goal. Okay, so that's one way to define what the dleave, what minimum distance you have on the boundary at the moment to the goal. What's the minimum distance at the moment? Another way to describe it is the distance your robot has to the goal if there was no block on the way, there was no obstacle on the way. So one way is defined between the current sense boundary to the goal. That's one way to define it. The other way is directly from your robot, not the boundary, from your robot to the goal if there was what? There was nothing on the way. So if I could fly over this obstacle and directly go to the goal, that's dleave, right? So here I'm using different points. Here this dleave is what? It's the square root of, if you call your robot P, location X and Y, this is simply xg minus x squared plus yg minus y squared. Okay, this is dleave, but this dleave is between a sense boundary. So what you have here is this end point. If you call this endpoint RP1 and the location of that is like XP1 and YP1, then this dleave here is the square root of what? Of course, X goal minus XP1 squared and then plus YG minus YP1 squared. Okay, and how do you get xp1 and yp1 based on x and y? So what you need is, if you have your current location and if you have the relative angle between your center of the robot to the point, so you know that point comes from this angle here and this distance d. D is the distance between P and that endpoint. So that's what your scanner gives you. Your scanner gives you a bunch of what? Angles, right? It gives you a bunch of angles and a bunch of distances, right? And the angle is measured with respect to one of the axes of the robot, right? So, for example, if you have this axis of the robot, which here is shown by angle theta, you can measure this angle. So this angle alpha and the distance d, right, can give you the relative location of the scan point to your current point. So if I want to say what is xp1 and what is yp1 here, they are equal to basically x, correct, right, which is the center of the robot with respect to the origin of the inertial frame, and then plus this distance d that you have, correct, this distance d with relative angle alpha, and then you have to project it back into the global. For that you need this angle theta. right? So here, depending on how you describe your coordinates, if you call, for example, this axis x and this axis y, so this is y of the robot and this is x of the robot, or if you want to stay similar to that, call this one x of the robot, that one y of the robot. So call this one y of the robot, call this one x of the robot. Right? Then your angle, if it's measured from the y-axis, or let's say you might measure it from the x-axis, so let me get rid of all of these extra ones and do a clean job. So that's x over, that's y over. The d is the distance that your scanner measured, this distance here, and alpha is this angle, right? Then this plus d cosine alpha, right? This is the coordinate of the point xr in the body attached frame, in the robot attached frame. That's not exactly what you want. So let me just do it this way. This is d cosine alpha, this is d sine alpha. These are the coordinates, these are the coordinates of the scan point in the robot frame. And now if you want to go back to the base frame, since your rotation is rotation theta with the z-axis, so if you want these, maybe I call them in the R frame. If I want them in the absolute frame, correct? This thing here is gonna be rotation z with angle theta times xp1 in the R and yp1 in the R, right? That's what you know from rotation matrices, correct? And then what? Plus, of course, x of the robot itself and y of the robot itself, which are these values. Correct? It's a homogeneous transformation. This is the translation part of it, this is the rotation part of it. Add them together and get the coordinate of what? The sense point in the base frame, in the inertial frame, and now these numbers can come here and here, and now you can calculate your d-leave. Okay, so this definition of d-leave is of course much easier. It doesn't need to really rely on your sensor, right, to do any transformation back to the global, because x and y are already measured in global, xg and yg are in global frame or inertial frame. So this definition is easier, right? But typically many applications, they go with this because this relates to the boundary, and d min also is related to the boundary, right? So it's better to compare the distance from boundary to the goal and boundary to the goal, not robot to the goal and boundary to the goal. So we typically go with the first definition, although we can also go with the second definition, but here I explain both of them. What's the meaning of each one of these two different definitions of the leave, or as I said, in some literature you call it the reach. So now with all that in mind, let's talk about the overall algorithm. What do we do? So here, as I said, I'm starting from start point to the goal point. I first go straight to the goal. Until what? I reach an obstacle. Now my LiDAR can scan something with the angle that it has and with the range it has. Now it fills some boundary. It knows that it cannot move any forward. So now it has to decide which direction to go, right? Now it has to decide whether it wants to go to this endpoint or this endpoint. Between these two, which one do I go? And then do the wall following. Which one? Here it tells you that between the two endpoints, RP1 and RP2, choose the one that is what? Choose the one that has a minimal value of the h function, the heuristic function, which has two parts, as I said. One of them is the distance from your robot to that endpoint. This d is the same d I showed you in the previous formula. This one comes from what? This guy comes from LiDAR. Okay, that's this d. The other distance from n to g, or from the endpoint to the goal, when you calculate the position of the endpoints using the same method I told you, now you calculate their distances to the goal by Euclidean distance, right? So that's this distance here in red. So what you basically measure is sum of these two. So between this one in blue and this one in black, which one is minimal? Whatever is minimal, you go toward that endpoint. So let's say, for example, here RP2 has a total of the two distances smaller than RP1. So when I get to point P, I'm not going to go straight anymore. I only go to one of these two endpoints that provides you the minimal distance. Okay, it provides you this. So I go to our RP2. Good. Now when I go here toward RP2, now I have to do the wall following. Good. So definitely here, going toward one of these two endpoints will tell me which direction to do the wall following, clockwise or counterclockwise, right? Let's say in this case, it might be that this point down here is closer than the top point up there. So if this point is closer, then I go in this direction, as you can see. So it is going down in this direction and coming to point D1. So it goes from what? H1 to D1, because initially it found a point here that was closer than a point here. So I went into this direction until you get to D1. Now, when you are doing wall following from H1 to D1, you have to keep calculating some numbers. What are they? You have to calculate your D min and D leave all the time, and you have to calculate the locations of the endpoints as well, right? So when you are here, let's say, for example, you are somewhere in the mid road. Let's say you are here. Again, you have that circle around you. And again, you have what? You have your LiDAR. And again, you have the endpoints. So you need to calculate the location of the endpoints all the time. You have to calculate what? The D min, which is the minimum of the distance you have observed so far between the boundary and the goal point. And for that, not only you need the endpoints, you also need what? Any other point on the boundary that you can sense, because one of them can provide you with the D minimum, right? And again, you can calculate your D leave either basically you calculate which one of these guys is the minimum, right? Because D leave, the definition of it, again, if you look at it, it is the minimum current distance, right? So you calculate your minimum current distance between all of these points that you can sense. That gives you D leave, and then compare the minimum value that you have here with all the minimums that you had in the past. The minimum of all of them will give you D min. So you keep going. If any of these gives you a number smaller than D min, means now one of these points is better than any point that you had in the past. and that means that point can be closer to the goal and give you a free way to the goal. So here, this dmin probably is calculated using direct distance from the robot to the goal. So this distance is calculated as dleave. Dmin is all of those distances, and dlive here is not going to be smaller than dmin until you come here. Now, this distance from D1 all the way to the goal is smaller than anything you had so far. So now you know you have found a point that is better than anything else. So maybe now it is time for me to let the wall go and what? Keep going straight to what? To the goal. So now I keep straight to the goal. Again, I reach the next obstacle. Again, I find two endpoints. The endpoints will give me one direction to go. Again, let's say here, 2 endpoints. I come down to here. Again, dleave is less than dmin. I keep going. Again, go straight to the goal, as you can see, until I hit here. Again, here I fill two points. This one looks closer to the goal than this one, so now this time I go up. And here I keep going until D3. Now again, leave is going to be less than all the dmins that I have observed so far. Again, I go straight. Again, I scan 2 points. This point looks closer, so I go. Again, I set free, and you see with this path, I can go from start point to the end point. So that's how your algorithm works. Keep going in a straight line toward the goal until either you directly reach the goal, which is very lucky, means nothing was in front of you, or you felt there is an obstacle. When there is an obstacle, you have to go into wall following. But how do you decide which side of the wall to go, which direction? You look at the endpoint that minimizes your heuristic function, right? Which we defined here. Which one minimizes this? You go toward that endpoint, and that tells you which way around the obstacle to navigate. And as you go around the obstacle and navigate, do the wall following, you continuously sense all of the points on the wall, calculate their locations using the method I showed you, using that rotation Z and everything, right? You find the distances between each and every one of these points to the goal, right? If any of them is less than whatever you had in the memory, you set that as the minimum. Also, you can define your distance, current distance of the robot, not the sense boundary, to the goal as dleave, or if you want, you can define the minimal distance that you have right now from any of the sense point to the goal as your dleave. And whenever dleave is less than dmin, which means you found a better point to toward the goal, now you can what? You can stop the wall following and directly go toward the goal until you hit another obstacle or you reach the goal, or if you go around and in none of these points there was a point that give you anything smaller than the minimum, maybe the algorithm cannot what? Reach, right? Why? Because your goal is trapped inside an obstacle. So this method will never fail unless your goal is completely enclosed. So if your goal like here is enclosed by something like this, let's say you extend this like that, so it's completely enclosed, then wherever you come, right? So let's say you come here and then now you sense this point and this point, and you decide this point is closer, so you go this way, and then try to do the wall following, right? And at some point probably you measure some minimal distance like this. This is the list that you probably can get close. Now there is nowhere as you navigate around this big obstacle that you can find any distance less than this dmin. So there is no place that you can set yourself free from the wall and go toward the goal, right? This was the best. And guess what? When it was the best, there was no clear path. So you went one full path around the obstacle. You could not find any better location to get in. And that means there is no way to get in. And so your algorithm would basically go through one full cycle, and the goal is what? Unreachable. So this is how this tangent bug is working. And now I want to show you a demo of this algorithm in practice. So here we go. You see? Now when it reached this point, it found that, well, now my D leave is less than the smallest D that I had ever in the memory. So now it is time for me to get what? Out of the wall and go directly toward the goal. Let me do it one more time. Take a look. You see here, this is probably the main D that it can measure here. And now that distance is going to be less than that. So if I can insert a bunch of points along this path, one of them was the closest ever to this point, and that is probably, since we started from here, I would say a point like this. A point like this guy was the closest point that you probably ever get to, right, to the goal. So D min is this distance here. This is D min, right? Let me insert the text box here for you. This is D min. This is the best you could go so far. But as you move to next point, next point, next point, and so on, look, these are the distances. So this is 1, correct? This is 1. This is 1. And these distances, all of them are bigger than this D minimum until you get to this point. When you get to this point, now your D, this D here, this last D, this one, this D is going to be what? Less than D minimum. So all of these guys were D leave, right? If I want to put something here, all of these guys were D leave. And these D leaves were all bigger than D minimum until I reached to this point. Now my D leave is less than D minimum. So now I know it's a good time to leave the wall and directly go toward the goal. Okay, so I assume that's quite clear here. Now I should be able to move this a little bit further. Maybe I can bring it down here, put it right below the start position. So if we go down, here is the start at 300 negative 550. Let's see if I can go right below that. Oh, it wasn't low enough. And you see, when it does the wall following, it's quite stupid. It doesn't look back because your sensor is only looking that area. Okay? And it goes one full round. Look, it did not even find it, I guess. Well, because I guess it is on an obstacle, that's the reason. So I need to go quite further down. Let's see. This is further. There we go. You see, this line in this dash line is dleave. That's what it is calculating. Now it goes to it. Okay, so this is called the Tengen-Bog algorithm. Hopefully, this demo was useful to you and explaining the terminologies in the algorithm. And I will see you in my next lecture. Thank you.